Good morning, students. So it's time to start new lecture of Math F211, Mathematics Third. So welcome in this lecture. So in last class, I have started second order linear differential equation. Audio video is okay.
Yes, sir.
Anyone
Yes,
please
sir.
reply? Yes. Thank you. So in last class, I have started the second chapter on based on second order differential equation. So last time we have discussed the general second order differential equation or linear differential equation is the d2y upon dx2 plus px dy by dx plus qx y is equal to rx. So this is the homogeneous non-homogeneous system of or non-homogeneous differential equation. When we put rx is equal to 0, then it become the homogeneous differential equation. There we have studied the three theorems. Theorem A, let Px, Qx, Rx be continuous function on closed interval AB if x naught is any point in closed interval AB, and if y naught and y naught dash are any number whatever, then first has one and only one solution yx on the entire interval such that yx naught is equal to y naught and y dash at x naught is equal to y naught dash. So means if condition is given to you, then we have the unique solution. Thereafter we have studied the theorem B. If yg is general solution of reduced equation means homogeneous equation, and yp is any particular solution of the complete equation, then yg plus yp is general solution of the first. That is the structure of the solution. Means for determining the non solution of non-homogeneous differential equation, we have to compute the general solution of homogeneous equation and particular solution of the non-homogeneous differential equation. Then we have to add up. Then we have to sum up. So that is the third theorem. Then after we have the theorem C. If y1 and y2 are any two solution of two means homogeneous equation, then c1 y1 plus c2 y2 is also solution of any for any constant c1 and c2. Means here the linear combination of the solution is also the solution of the homogeneous differential equation. So this much we have done in last class. Now next to this, in each of the following cases, use inspection or experiment to find the particular solution of reduced and complete equation and write down the general solution. So here we have to determine the particular and the general solution. So let us have the y double dash is equal to e to power x. So we know that if the equation is if equation is given to you y double dash is equal to e to power x, so its reduced equation will be the y double dash is equal to 0. So we can say y is equal to 1 and y is equal to x be solution of let's it is complete equation in 1, it is 2, so solution of the 2. So by the theorem C, by theorem C, y is equal to C1 into 1, C1 into 1 plus C2 into x, C2 into x be also solution of 2, solution of 2. And here if you assume y is equal to, right, so here we have computed the general solution of the reduced equation. Then we say y is equal to or you can say yp is equal to e to power x. So yp dash is equal to e to power x and yp double dash is equal to e to power x. So here you can see, from here you can see that e to power x is equal to e to power x, it is coming. So it means yp is the particular solution of the complete equation and yg is general solution of the homogeneous equation, reduced equation. So y is equal to yg plus yp. The theorem b, that is the c1 plus c2x plus e to power x b, general solution b, general solution of the complete equation 1. So in this way we write the solution of second order linear differential equation.
So could you repeat this part once again? The question you did right now.
What is question or solution part?
The solution part, the theorem you used, I mean the way you used it. Could you just repeat the solution once more?
I'm saying that we have seen y is equal to 1. Y is equal to 1 means let's say it is the y1, it is the y2. So y1 dash is equal to 0, y1 double dash is equal to 0, right? So when we put here the 0, so it will give you 0 is equal to 0, correct? When y2 is equal to x, so y2 dash is equal to 1 and y2 double dash is equal to 0. So again the y2, when we put here the y2 is equal to 0, so it will give you 0 is equal to 0. It means y1 is equal to 1, y2 is equal to x, be the solution of the second one. So by the theorem c by the theorem c, yes, by the theorem C, if y1, y2 are any two solution of reduced equation 2, then c1 y1 plus c2 y2 is also solution of for any constant c1 and c2. So that's we have used here. So c1 into 1 plus c2 into x be also solution of the reduced equation 2. Then we take yp, a particular solution, e to power x. So we check whether it is a solution or not. So yp dash is equal to e to power x, yp double dash is equal to e to power x. So when we put in this in the main equation or a complete equation or non-homogeneous equation, you will get the e to power x is equal to e to power x. So now the what is the b theorem b state theorem b state Theorem B state that if Yg is general solution of reduced equation 2, means C1 plus C2x, and Yp is any particular solution of the complete equation, means e to power x, then Yg plus Yp, C1 plus C2x plus e to power x is the general solution of the first.
Sir,
Clear now?
Sir, sir, the
sir,
general
Huh?
solution will be y1 is equal to c. Sir, you have written y1 is equal to 1. Sir, for y double dash equal to 0.
That's my you can say y1 is equal to 1 or c, and both will work.
Okay, sir. Yes, sir. It will give.
Actually that we can handle here, na.
Yes, sir. Multiplication will be constant. Okay, sir.
That we can handle here, na.
sir,
Any other doubt?
sir. So since our second equation is y double dash equal to 0, so y1 and y2 can be taken anything,
Y1 and
any
y2
constant.
which satisfy the
That
y double dash is equal to 0.
so only this
I'm
condition does not provide infinite possibilities. Well, we
pardon,
should
I'm
have
not
taken
get.
both constants. I'm like y1 is
No, no,
equal to 1
both.
and y2 is equal to 2.
No, no, in that I will come. Just wait a bit. In that I will come. Why we cannot take
Okay.
like that? I'm coming there. So let us have this question: x minus 1 y double dash minus x y dash plus y is equal to 0. So in this case, if you write in the In this case, if you write in the standard form, so it will give you y double dash minus x upon x minus 1 y dash plus 1 upon x minus 1 y is equal to 0. So it means this is what it is the p, this is what it is the q. P function of x, function of x. Y double dash plus px y dash plus qx y is equal to 0. Means here rx, it is the rx is identically 0, means given system is the homogeneous system or reduced equation. So in this case, if you check y is equal to x, if you check the y is equal to x, so let y1 is equal to x, so y1 dash, y1 dash will become the 1 and y1 double dash will become the 0. So here when we put, it is the 0, it is 1, right, it is 1. So and y is equal to what, y is equal to x, it is x. So you will get the x minus x upon x minus 1 plus x upon x minus 1, that will give the 0. Means y1 is equal to x will satisfy the solution. Then after, if you take the y2 is equal to e to power x, y2 is equal to e to power x, so y2 dash will be the e to power x and y2 double dash will be the e to power x. So when we put y double dash as a e to power x, y1 dash as a e to power x, and y is equal to e to power x. So you will see it will give you again the 0. It means we can say y is equal to x and y is equal to e to power x, or y1 is equal to x, y2 is equal to e to power x are the solution of the first. So by the theorem C, y theorem C, y is equal to c1 y1 plus c2 y2 will also be the solution of the 2. Now you can say how you have recognized that y is equal to x, y is equal to e to power x are the solution. So for that I have given here the hint in the box. I have given the hint. If 1 plus p plus q is equal to 0, then by inspection you can say y is equal to e to power x will be the solution. So here you can see 1 plus p plus q. So 1 plus p, p is what, minus x upon x minus 1, x minus 1 plus q, that is the 1 upon x minus 1. So it will give you is equal to 0, means it satisfies the first condition. So y is equal to e to power x will be the solution. Similarly, 1 minus p plus q is equal to 0, then y to power y is equal to e to power minus x will be the solution. Generalize, if you generalize this, so a square plus p into a plus q is equal to 0, then y is equal to e to power ax will be the solution. Similarly, if p plus qx, p is what, p is the minus x upon x minus 1 plus qx, q is what, 1 upon x minus 1 into x, qx. If it is equal to 0, then we say y is equal to x will be the solution. Similarly, 2 plus 2px plus q, x square is equal to 0, then y is equal to x square will be the solution. And if m into m minus 1 plus pmx plus qx square is equal to 0, then y is equal to x to power m will be the solution. So by inspection, right, for the easy problem you can determine in this way also.
And sir, what about y1? We can take x or 1.
Y1 means anyone you
You
can take,
provided,
you can write na, you can write as a means y1 and y2.
no, I
for
mean
for
for
example,
every form
in this
you gave.
question, in this question we have written y is equal to x is the solution, y is equal to e to power x is the solution. So anyone you can assume
Okay, so
y1 and
second one
y2.
we will choose. आपने एक दे
Then
दिया, एक y दे दिया. We want y1 y2. आपने एक दे दिया,
huh,
दूसरा हमारी चॉइस है.
huh, it is your choice. Means you are saying na, means here we have the y1 is equal to x or y2 is equal to e to power x, or
Yes, sir.
you can say that y1 is equal to e to power x, y2 is equal to x. You have to write the two solution, then their linear combination is also the solution. That's I am writing here.
Okay.
Yes, any doubt? Now, if we have y double dash minus y is equal to sin x, so we know that y double dash minus y is equal to 0 will be the homogeneous equation. So you can check y is equal to e to power x, y is equal to e to power minus x will be the solution of the two. Means if I'm saying that y1 is equal to e to power x, so y1 dash is also e to power x, y1 double dash is equal to e to power x. Similarly, y2 is equal to e to power minus x, so y2 dash is equal to minus e to power minus x, and y2 double dash is equal to e to power minus x. So you can check e to power x and e to power minus x will satisfy this equation clearly. So by the theorem C, we say that general solution will be the C1 e to power x plus C2 e to power minus x be the solution of, so be the solution of 2, solution of 2. Now if you check y is equal to minus half sin x, minus y is equal to minus half sin x, so y dash will come minus half cos x, and y double dash will come minus half, minus minus plus half, and here we have the sin x. So when we put here we have the half sin x, half sin x, here also we have the half sin x, so half sin x minus half sin x will be the no uh, uh, means here we have half sin x, here we have to put the half sin x, just here I am writing y double dash minus y is equal to sin x. So here we have the half sin x, and here we have the minus of minus half sin x, half sin x. So that will give you sin x. So sin x is equal to sin x, it is coming. So it satisfies the given equation. So that will become the yp. So it will become the yp. So the general solution by the theorem B, it will be the yg plus yp. So c1 e to power x plus c2 e to power minus x minus half sin x will be the general solution, solution of the first, solution of first. Now if we have the x cube y double dash plus x square y dash plus xy is equal to 1. So if you write in the standard form, if you write in the standard form, if we have x cube y double dash, x cube y double dash plus x square y dash plus x square y dash plus xy is equal to 1. So if you write in the standard form, it will become y double dash plus 1 upon x y dash plus 1 upon x square y is equal to 1 upon x cube, 1 upon x cube. So right hand side is of the form, right hand side is of the form 1 upon x cube, and left hand side is equal to right hand side. So this is also should be of the form 1 upon x cube. So for that purpose, if you take the y is equal to c upon x, if you take y is equal to c upon x, so y dash will come minus c upon x square, and y double dash will come 2c upon x cube, 2c upon x cube. So when we put y double dash as a 2c upon x cube plus y dash is equal to minus c, so it will become the 1 upon x and minus c upon x square plus 1 upon x square plus 1 upon x square, and y is equal to c upon x, c upon x is equal to 1 upon x cube. So 1 upon x cube, 1 upon x cube everywhere we have. So here we have the 2c minus c plus c is equal to 1. So here we cancel out. So c is equal to 1 by 2. So you can see, So y is equal to 1 upon 2x will be the solution of the given equation. So sometimes whatever the right hand side, accordingly we have to judge what can be the form of the solution. So here we have the c is equal to half, right?
Sir, why we
Similarly,
need
if
to
we
do this?
actually we want the solution structure, so I uh, I want to convey here what can be the structure of the solution. From the given equation, how you can recognize what can be the structure of the, what is the shape of the solution? X to power n, x to 1 upon x to power n, or it is the sine of x, it is the cos of x, it is the log of x, what can be? So few simple equation, from the few simple equation I want to convey that can be the structure that you can judge.
Excuse me, sir. So y
Yes.
is equal to 2 by x is the general solution or like the particular solution?
When you are writing the c upon x, then it is the general solution. If it is the one, when we put c is equal to 1 by 2, then it is a particular solution.
So the general solution equation would be y is equal to c upon x plus 2 upon x.
No, no, that is not. Here, when we are computing for the complete equation, or for the non-homogeneous equation, then it is the particular solution. For the general solution, we have to keep the right hand side is equal to 0.
Okay, sir.
And for that, we have the another solution.
Okay.
Means for the homogeneous system, we have to keep this as a 0. So now we have the homogeneous equation, and for the homogeneous equation we compute the two solution, c1 y1 plus c2 y2, then it will be the general solution.
Okay, so for this question, we'll only get the particular solution.
No, no, we can compute here. Just I am giving you, later on I determine the what will be the y1 and y2 by the different method. Just I want to convey what is the structure of the solution. Okay, how we can write the solution, right? Later on I will rehandle this when with the well known methodology. I will find the solution of the y1 and y2.
Okay, sir.
Let us have this equation, y double dash minus 2y dash is equal to 6. So 6 is what? 6 is what? It is a polynomial. It is polynomial. It means right hand side should also be the polynomial. Then you can compare the polynomial is equal to polynomial. So in for that, what we can do? If you take the y is equal to cx, then y dash is equal to c, and y double dash is equal to 0. So when we put here, it will become the 0 minus 2 cx is equal to 6. Right? Cx is equal to no, c is equal to 2c is equal to 6. So c will come minus 3. Right? So in that case, you can say that y is equal to minus 3x.
Sir, so to match the LHS, we take the lowest order differential term. Maybe it's y dash or y, and according to that we keep y.
Yes, means actually whatever the right hand side, accordingly we have to decide what can be the y.
Okay, sir, got it.
Then only you can equate, no? For example, if you have the y double dash minus 2y is equal to sin x, y double dash minus 2y is equal to sin x. So here we have the trigonometry. So trigonometry can be equate with the trigonometry only. So at that time we assume that y is equal to a sin x plus b cos x. So y dash will be the a cos x minus b sin x, and y double dash will be the minus a sin x plus or minus b cos x. So when we put this value here and this value here and compare on both side coefficient of the sin x and coefficient of the cos x, you will get the value of the a and b. So that will be the solution. So just depending over the right hand side, what can be the left hand side, that here you have to recognize. But we have the well known method with which we will determine the solution. Only the main thing, you have to write the solution in the form y is equal to c1 y1 plus c2 y2 plus ypx. This you have to write. That is the main thing.
For
Now
both homogeneous and non-homogeneous.
for the homogeneous this much only, for the non homogeneous this only.
Okay.
With including the rx, we increase this particular solution. Right now question arise, because you have already asked this question, that every y1 and y2 can be written as c1 y1 plus c2 y2 for the solution of the homogeneous equation. You have already asked this question, right? Y1 is equal to 1, y2 is equal to 2. So can we write the c1 into 1 plus c2 into 2 as a solution of the homogeneous equation, right? Or I have written the c1 is equal to 1, y2 is equal to x. So we should write the c1 into 1 plus c2 into x. So what can be the correct one? So for that we have the most important theorem, right? This theorem. So here we will study the most important theorem, right? Theorem A. So before that, we have the two important concepts, linearly dependent and linearly independent. So what is the linearly dependent and what is the linearly independent? So if we have the two function fx and gx, and here we have the two function fx and gx. So when we say fx and gx are linearly dependent, when fx is constant multiple of gx, when fx is constant multiple of gx, then we say f and g are linearly dependent. And if it is not, then they are the linearly independent. What is the other definition in the linear algebra you have studied? If you write the if you can write the non-trivial linear combination of fx and gx, right, is equal to 0, then it is the linearly dependent, otherwise it is the linearly independent. Means if we have the c1 fx plus c2 gx, that is the linear combination. If it is equal to 0, and these c1 and c2, c1 and c2 are non-zero, if it is the non-zero, then we say that c1 and c2 are right. So c1 and c2 are the linearly dependent, right? Otherwise it is the linearly independent. If it is the zero, if it is the zero, then it is the li. So here, if fx is identically 0, means we can write as a c1, right, into fx, that is the 0, plus c2, right? So c2 into gx is equal to 0. So when fx is identically 0, you can take this as a non-zero. You can take this as a non-zero. So it will come the, you can take this as a, not non-zero. You can take it as a zero. So when it is the zero, it will become the LD. It will become the LD. Means it is the, I have wrongly written. It is the Li. This. If it is the non-zero, then Li. If it is the zero, then LD. Means if the fx is identically zero and gx is not zero, gx is not zero. So if you compute the linear combination, so c1 fx plus c2 gx is equal to 0, and if it is the identically 0, if it is the identically 0, so you can take this as a non-zero, you can take this as a non-zero and this as a 0, then non-zero into 0 plus 0 into non-zero, right? Non-zero into 0 plus 0 into non-zero will give you result 0. So here we have the non-zero, here we have the non-zero, so it will become the, right, it will become the LD. So here we have the gx is the LD to the 0. So from here, the general solution of the homogeneous equation, general solution of the homogeneous equation. So here we have the theorem A, very most important theorem. Let y1 and y2 be linearly independent solution of homogeneous equation. Let y1 and y2 be linearly independent solution of the homogeneous equation. Y double dash plus px y dash plus qx y is equal to 0 on the interval, on the closed interval a comma b. Then c1 y1 plus c2 y2 is the solution, is the solution. But now I am claiming that is the general solution. For being a general solution, y1 and y2 must be linearly independent. For being a general solution, for being a general solution, right, c1 y1 plus c2 y2, y1 and y2 must be the linearly independent, independent of the first on closed interval a comma b, in the sense that every solution of the first on this interval can be obtained from 2 by suitable choice of the arbitrary constant c1 and c2. So that is the theorem. Means every, for example, if I have the any differential equation and y1 is equal to 1, y2 is equal to 2, then c1 into 1 plus c2 into 2 b solution, b solution, but not, but not general solution, but not general solution. Why not general solution? Since y2 is equal to what? 2 constant multiple of the y1. Y2 is the constant multiple of y1, means not Li, not Li. So for writing the general solution, for writing the general solution means y1 is equal to 1, y2 is equal to x. So we can write c1 into 1 plus c2 into x, b general solution, be the general solution. So general solution, why we can write it as a general solution? If you compute the y2 that is the x is not constant multiple of the y1, it means y1 and y2 both are the Li. So when the y1 and y2 are Li, then only c1 y1 plus c2 y2 be the general solution of the homogeneous differential equation. And for writing the y is equal to yg plus yp, this yg must be the general solution of the homogeneous equation, then only you can write the general solution of the non-homogeneous equation. So for writing the yg, we compute the two solution, and both solution must be Li, then only c1 y1 plus c2 y2 will be the solution. Otherwise c1 y1 plus c2 y2 will be the solution only, not general solution. If for any equation, y is equal to sin x be the solution, so definitely 2 into sin x, y is equal to 3 into sin x, all are the solution of the same differential equation. But for writing the general solution, we have to determine other li solution, so this theorem states this. So now, in understanding this, any doubt? So now we will prove this. Its proof is little lengthy. We will prove this theorem using the certain lemmas. So using the certain lemma, there are the three things: axiom, lemma, and theorem. Axiom is always the true statement. Lemma is the statement which we prove for the proof of the theorem, and theorem is the statement which require the proof. So lemma generally is the statement which we generally use for the proof of the theorem. So here we will prove this theorem by using the certain lemmas. Let we assume that we have the two solutions. Let yx be the solution of the first, y double dash plus pxy dash plus qxy is equal to 0 on closed interval ab. We have to show that constants c1 and c2 can be found so that c1 y1 plus c2 y2 is equal to the yx. c1 y1 x plus c2 y2 x is equal to yx. Then only we can say that it is the general solution. So here, by the theorem 14a, what are the theorem 14a? For the given particular point, means by the theorem a section 14 on page 82, we know that the solution of the first over all interval ab is completely determined by its value, that is the y naught, and the value of its derivative y naught dash at the single point, that is the x naught. So here we have the two solution, c1 y1 x plus c2 y2 x, and another solution is the yx. If at the particular solution, at the particular point, if at the particular point we write in this way: c1 y1 at x naught plus c2 y2 at x naught is equal to y at x naught, c1 y1 dash x naught plus c2 y2 dash x naught is equal to y dash x naught. Right? If we can write in this way both the solution of the first on the interval ab, then for some point x naught in ab we can find c1 and c2, so that so if you can determine the c1 and c2, if you are able to determine the c1 c2 such that these two equations are equal, then only we can say y is equal to c1 y1 plus c2 y2. Because in the theorem a state that if any solution satisfied for the particular point, if it satisfies the condition, then we have the unique solution. Unique solution means we have assumed the two different solution, but if they are equal, at the particular point, then we say they are the unique. So now for determining the c1 and c2, what must be the when the solution of these two equation will exist. This is the system of equation with unknown c1 and c2. So when this system of equation will exist, solution of the system of equation will exist by the matrix theory: y1 y1 y2 y1 dash y2 dash must be non-zero. If it is the non-zero, then only the above system of equation has the answer or solution. c1 and c2 you can determine. Clear this part? So Some doubt? Anyone please reply.
No, sir.
Yes, what the doubt? I'm saying that if we have this equation, we can write in the matrix form like this: y1, y2, y1 dash, y2 dash, c1, c2 is equal to y and y dash. We can write, so c1, c2 can be written as inverse of this into y, y dash. So when this inverse exists, when this inverse exists, when this determinant is non-zero. So for the existence of the solution, for the existence of the solution for the this system of equation, this determinant should be non-zero. So that here it is written. So for this to be solvable for C1 and C2, the determinant y1, y2, y1 dash, y2 dash, right? Y1, y2 dash have a different value from the zero. Means it should be non-zero. It should be non-zero. So now we determine when it is the non-zero. Now we determine the condition when it is the non-zero. So we try to show that whatever the, and this determinant we denote by the w, which is a function of y1 and y2, and it is known as the Wronskian. It is known as the Wronskian. So w is equal to y1, y2, y1 dash, y2 dash, and it is known as the Wronskian, right? So here we try to show that whether the Wronskian vanishes at x naught or not. So now we have to see that whether this Wronskian is non-zero or zero. That we have to check. That we have to check whether the Wronskian is non-zero or zero. So for that we have the first lemma. First lemma is, if y1 and y2 are any two solution of the first on closed interval AB, then their Wronskian on Wronskian W is either identically zero or never zero on the closed interval AB. Means on the closed interval AB, we cannot say at this point W is zero, at this point W is not equal to zero, at this point W is equal to zero. That cannot happen. If Wronskian is zero over all complete AB, for all point of the x between AB, W is equal to zero, or for all point W is not equal to zero. Never we can have the fluctuation. If for some point of x it is zero, for some point of x it is non-zero. That cannot happen. Means Wronskian is either identically zero, means everywhere it is zero, or never zero, means nowhere it is zero. So how it can come? Means we cannot say कि for some x naught belongs to AB, this determinant is zero or non-zero. Either it is zero everywhere or it is non-zero everywhere for all the x's. So here, uh, so we have the proof of this. W is equal to what? W is equal to determinant of the y1, y2, y1 dash, y2 dash. So W will be the y1 y1 W is equal to y1 into y2 dash minus y2 into y1 dash. So from the W you can compute the W dash. W dash will be the y1 y2 double dash plus y1 dash y2 dash minus y2 y1 dash y1 double dash plus y2 dash y1 dash. that so it will cancel out. Y1 dash y2 dash will cancel out. So here we have the w dash as a y1 into y2 double dash minus y2 into y1 double dash, and y1 and y2 are the solution of the first. It is given to you, they are the solution of the first. It means it satisfies the given homogeneous differential equation. Y1 means it satisfies the given homogeneous differential equation. Y1 double dash plus px y1 dash plus qx y1 is equal to 0, because our equation is what, y1 y double dash plus px px y dash plus qx is equal to qx y is equal to 0. So in place of the y1 will come, in place of the y2 will come. So we have the y2 double dash plus px y2 dash plus qx y2 is equal to 0. Now, so here, if it is the second and third and fourth, if it is the third and fourth, so multiply the third by the y2 minus 4 by the y1, 4 by the y1. So what you will get? You will get the, it means in this you multiply with the y2 and in this you multiply with the y1. So you will get the y1 y2 double dash minus y2 y1 double dash plus p y1 y2 dash plus y2 y1 dash plus q y1 y2 minus y1 y2. So that will cancel out, is equal to 0. That will cancel out and it is equal to 0. So here we have the this, and this is what, this is from here, this is from here, it is the w dash, this is the w dash. So we write dw by dx, and what is this, what is this, this is the w. So dw by dx plus pw is equal to 0. So now it is the first order differential equation. So it can be written as dw by dx is equal to minus pw. Separate the variable. So dw by w is equal to minus p dx. Integrate on both sides. So ln w is equal to integral minus p dx. So w will be what? C and plus ln c, plus ln c. So w is what? C e to power minus integral p dx. So w, we have the w is equal to c e to power minus integral p dx. So this is the exponential function. Exponents, you know about the exponential function that it never zero. So w is identically 0. W is identically 0 only when c is equal to 0. If c is not equal to 0, then w is never 0. Then the w is never 0. So depending over the c, we have the this thing. Then we have the lemma 2. If y1 and y2 are two solution of the first on closed interval ab, then they are linearly dependent on this interval if Wronskian is identically 0. Means y1 and y2 are ld, then Wronskian is identically 0. If Wronskian is non-zero, then you can say y1 and y2 are li. Li means c1 and c2 are non-zero. C1 and C2 are non-zero, right? C1 and C2 in linear combination C1 y1 plus C2 y2 are the non-zero. So uh, and we have seen Wronskian is either zero everywhere or non-zero everywhere, non-zero everywhere. Never we have the mixing. It means never we have the mixing of the LD and LI. Either the y1 and y2 is completely LI or completely LD, right? Either the y1 and y2 are completely Li or completely LD. If it is the completely Li, then y is equal to c1 y1 plus c2 y2 will be the general solution. Otherwise you cannot write the general solution. So proof of this we continue in the next class. Time is over. Any doubt till now?
Sir, can you scroll up a bit?
In next class also I will rebrush all the things. Actually, this is little lengthy proof. Okay. Any other doubt? What do you want to see here? Clear this part?
Thank you, sir.
Yes, welcome.